I work mainly on philosophical and foundational problems of modern physics, especially of quantum physics, including relativistic quantum field theory. But I've also done work on more general problems that cut across disciplines and sciences. And one such more general problem concerns the causal explanation of correlations. Now, with slight exaggeration, one can say that sciences begin with discovering correlations and end with explaining them. And correlations are everywhere, really. It's not very difficult to find them. There is correlation, for instance, between smoking and lung cancer. There's correlation between level of education and level of income. Typically, people who have more education earn more. There's also correlation between the number of open umbrellas and windshield wiper movements on cars. There's also correlation between bread prices in Britain and water levels in Venice. Both have been on the rise in the past 2 centuries. And there's also correlation between values of a certain quantity called spin if measured on a pair of particles that have been prepared in a specific quantum states. These are the so-called and famous Einstein-Podolsky-Rosen correlations, and they have been measured using very sophisticated measuring devices by physicists located in different parts of space. Now, the reason why we and scientists in particular are interested in correlations is because correlations are signs of causal connections. And there's a very famous philosophical principle which states that there is no correlation without causation whatsoever. But the problem is that the causal connection which this principle claims is behind every correlation is not necessarily a direct causal link between the correlated entities. It might very well be the case that the correlation is due to some third factor, a so-called common cause, which explains the correlation by being related to the correlated entities in a certain causal way. For instance, in the case of the correlation between the number of open umbrellas and the windshield wiper movements, it is raining that explains the correlation. It's not the case that opening the umbrella causally affects the windshield wipers on the cars. That's not at all the case. It's the raining which is the explanation. In the case of the correlation between bread prices in Britain and water levels in Venice, we also do not expect it to be explainable by a direct causal link between the bread prices and the water levels. After all, the water levels in Venice don't have to do anything with the bread prices in Britain. But in this case, it's not at all clear what a possible common cause explanation could be. It is even less obvious in the case of the so-called Einstein-Podolsky-Rosen correlations how to explain them causally, and this has been subject of an intense debate ever since these correlations have been predicted and measured by physicists. So in general, it is an extremely difficult problem to decide whether a certain correlation is due to a direct causal link between the correlated entities or whether it is due to a third factor, a common cause. And my research, which I have done in collaboration with some colleagues, concerns this issue. And the type of questions which one can ask in connection with this problem are the following. Is it possible, in principle at least, to explain a correlation always in terms of some common cause? Possibly in terms of some common cause which is hidden in the sense of not being part of the original theory that discovers the correlation. Is it possible for a theory to be common cause complete in the sense of providing a causal explanation of all the correlations it predicts? Are our theories causally complete in this sense? And if they are not, is it possible in principle to make them common cause complete or causally complete by extending them, by making them richer, so that the richer theory is rich enough to provide the causal explanation we are asking for. Also, it's an interesting question if there are good tests for deciding whether a certain theory is causally complete or not. Also, questions like, are there structural properties of theories which are directly relevant for their causal completeness or not? Now, the characteristic feature of this kind of research is that these and similar questions can be translated into precise mathematical concepts and problems and questions using concepts of probability theory. And once these problems have been sharply formulated, they can be analyzed with the techniques of probability theory, and then the proven theorems and results can be interpreted philosophically. So this kind of research is really very close to the sciences, is continuous with them, and the results obtained are directly relevant for the sciences, not only for the physical sciences, but for every science which uses probability theory.